Okay, I think we have to start. Welcome to one of the last sessions here, for today at least. This is the session on text, language, and image data. My name is Steffen Koch from the University of Stuttgart. I think by now you know how it works. Please state your questions on Slido. And without further ado, I think we can start with our first talk, which will be a virtual one. The speakers are Wai-Kai Yang and Jen Lee. And maybe we can just right away switch to their presentation.
This is Jen Lee. Today, I will introduce our work, a unified understanding of deep NLP models for text classification. Text classification is a fundamental task in natural language processing. In recent years, different deep NLP models have been proposed to improve the performance of text classification tasks. To better understand the models of different architectures, there is an urgent need for a unified understanding. However, a key challenge is how to understand working mechanisms of different models in a unified way. Another challenge is how to help users explore models and identify models' deficiencies based on the unified understanding. To tackle these two challenges, we first proposed an information-based sample interpretation method to understand different models in a unified way. We then developed a three-level visualization that enables users to smoothly navigate from the overall performance at the corpus level to the detailed information at the sample and word level. Based on them, we developed Deep NLP Viz, an interactive visual analysis tool to help model developers understand different models, identify their problems, and make improvements. Next, I will introduce an overview of our system. Given training data and trained model, the information in each training sample is extracted. The extracted information can be divided into two categories. Introvert information analyzes the word contribution to the prediction, and introvert information captures the relationships between words. This extracted information is then fed into a three-level visualization. At the corpus level, the class view reveals the overall model performance on all classes. The distribution view explores the prediction distribution and identifies samples and words of interest. Selected samples are displayed in a sample list. User can select a sample and explore how models process it. Associated words are displayed in the word contribution view. Users can also analyze the word of interest in the context. Next, I will introduce our unified information-based measure. The previous method estimates the word contribution to prediction, but it still has two limitations. First, it fails to reveal the polarity of the word. Without the polarity, we can only know that both Google and IPO are important. With polarity, we can identify that Google was the root cause, that this sentence been mispredicted as science or tech news. Second, the previous method fails to capture the interword information, which is important to understand how an NLP model learns high-level features. We proposed two methods to extract the learned phrases and non-adjacent word relationships, respectively. For more details, please refer to our paper. Then, we introduce our three-level visualization. At the corpus level, we employ a standard confusion matrix in the class view. Since it is easy to implement, we focus more on the distribution view. This view reveals the prediction distribution and identifies important samples and words for further analysis. we developed a hexagonal heat map for samples, which integrates the prediction score with a one-dimensional t-SNE projection. A hexagonal represents a set of samples that are classified correctly, and a cross represents a set of misclassified samples. The color encodes the class of samples. The darker color, the more samples it represented. A group of representative words is also displayed. At the sample level, the sample list allows users to examine multi-samples in terms of their content, class labels, and predictions. After identifying the samples of interest, users can analyze how NLP models process it through layers. The design of information flow was inspired by storyline visualization. Each word is represented by a line, and the introvert information is encoded by the line width and colors. The width encodes the magnitude of the contribution, and the color encodes the polarity. To facilitate the exploration, the layout of the storyline needs to preserve both stability and readability. Stability prevents the y-coordinate of a line from changing dramatically when its context vector does not change much. Readability measures how clear and easy it is to understand the relationships between words in a sample. At the word level, it allows users to examine the contribution of words and their changes across layers, as well as its context. The word contribution view helps identify the words and layers of interest based on the word's contribution to different layers in the model. After identifying the words of interest, the word context view facilitates the understanding of a word by revealing how the model processes it based on its context. Then, we introduce a case study to demonstrate how deep NLP with helps understand and diagnose BERT for sentiment classification. In the distribution view, the prediction scores have long-tailed distributions. Samples with low confidence are horizontally closer. Keywords extracted have relevant sentiment. In the word contribution view, the model increasingly focuses on words with sentiment tendencies. In the last two layers, most words have strong positive or negative meanings. Click to show the words with significant contribution changes. The contribution of loves and care increases rapidly in the last few layers. The word care contributes more to negative predictions. Examine its word context. Care is embedded more in a negative context. The more frequent presence of care in negative samples causes this result. Select a representative sample with high confidence. Context received is formed with a neutral sentiment. What's the best the context received is then formed together and turns positive. It turns negative at layer 7 with the information transfer of if. The turning structure is correctly interpreted. Then it transfers the information from the second half of the sentence to CLS and determines the negative prediction. Select all the misclassified samples. Examine the important words in predicting these samples. The word superficial remains strongly negative but turns positive in the last layer. The conflicting labels make the model confused. Correct the labels. After correcting 4 labels and inserting adapter modules, the model performance increases. To conclude our work, we present deep NLP with to facilitate a unified understanding of deep NLP models. This method is built upon an information-based measure and a 3-level visualization. In the future, we plan to extend deep NLP with to other NLP tasks, such as text summarization and machine translation. Integrating interactive visualization with machine learning to refine the model semi-automatically is another interesting direction. Thank you for listening. I'm happy to answer any questions.
Thank you for this fine presentation and also for the fine paper. Let's thank the speaker. And before I ask the first questions, please be reminded that you can ask questions in Slido, or if you don't want to do that, please come up to one of the microphones and state your question there. Okay, so maybe let's see if there's anything on Slido yet. There is one. Great work. It seems that the neural network you used in your case study is an auto-attentive model. Did you try your method with an RNN, for example?
Yeah, we also try our work on an LSTM model, and we make a comparison between the LSTM model and the BERT model, and find the benefits of BERT model. Why BERT model is better than LSTM model. And then we make a model distillation, and use the BERT model to refine the LSTM model.
Okay, thank you very much. And there is another question, maybe a brief answer for this one. Can this work be extended to other NLP tasks than classification?
Well, a good question. Our work, in this work, we use text classification for illustrate how our work understand deep NLP models. As we know, the deep NLP models is a feature extractor. It can extract the low-level features and high-level features, and for different tasks. For example, the text summarization, machine translation, and the question answering, these tasks are also classification tasks. So our work have possibility to extend those tasks, but there are still a limitation in these tasks. The class number are very large, and the scalability, we need to make new design.
Okay, yeah, I understand.
Okay, to solve the problem. Okay.
Thank you very much. Let's thank Jen Lee again. And now we have another talk in person this time about editext, explaining neural networks by exploring text classification decision boundaries. And our speaker is Alexis Delaforge.
Thank you. Hi everyone, I'm Alexis Delaforge, PhD candidate at the University of Montpellier in France. Today I'm going to present my work on the visualization of the decision boundary of neural networks for a text classification task. In this work, we focus on the binary classification of text. Our goal is to propose for any types of neural networks different information, allowing to explain the prediction and thus to tend towards a greater interpretability of these networks. In 2019, Francisco Rodriguez and al. Proposed to visualize for many classifiers the decision boundary using dimensional reduction techniques. Before your eyes is the decision boundary of a CNN for a binary classification of pictures. The dataset used is linearly separable. Some dimensional reduction techniques have proposed satisfactory results, UMAP for example, or TSNE on its left, but none of them propose the visualization of the boundary as a straight line, even if the dataset is linearly separable. The problem is, in the real world, datasets are not linearly separable, and so the problem is more complex. Moreover, if we plot data elements in this view, the distances to the decision boundary are not faithful to the distances in the representation space constructed by neural networks. Why do we need to have faithful distances? In practice, for a binary classification task, the neural network classifier predicts a value between 0 and 1 thanks to the sigmoid function. Thus, the distance between the data elements and the decision boundary are an information about the uncertainty of the neural network concerning its predictions. As I said before, UMAP proposed a satisfying solution from the data entry space. Nevertheless, the representation space built by neural network is more interesting because it disentangles the data. Depending on the size of the dataset, many elements may exist and saturate the visualization of the decision boundary. That's why we focus on subspaces of the representation space to explain prediction. We construct these subspaces and call them localities. Localities are then areas of the representation space where data elements lie close to each other. To construct them, we use the classifier component of the neural network, here in pink. We project the data element onto the decision boundary, as this boundary is an hyperplane in the data representation space. Then we use representation and projected representation to construct a proximity graph using the UMAP method. We apply several steps that I will not describe here to divide the proximity graph into several locality graphs. Each locality graph corresponds to a string graph in the overview of our tool. Our tool for explaining prediction is called EBText. It stands for Explanation by Boundary Exploration for Textual Data. In this overview, users can order localities to explore the text representation space and find localities that are relevant to analyze. Each string graph represents a locality and gives information about the distribution of data around the decision boundary, the gray line in the view. It also gives information about the quality of the classifier in this locality and the number of elements in this locality. Once a locality is selected, EBText offers a three-panel view of that locality. On the left, the subview of the decision boundary displays the boundary as a line and the surrounding data elements. The distances between the boundary and elements are faithful to the distances in the representation space constructed by neural networks. Thus, data that are close to the decision boundary has a high uncertainty, and data that are far away from the decision boundary has a low uncertainty. This subview allows users to select a data to visualize paths from this data to the decision boundary. The black links represent direct neighborhood links, and the blue links belongs to paths from the selected data to the decision boundary. To produce the decision boundary subview, we perform steps that ensure that data close in the representation space will be close in the decision boundary subview. In the center of the locality view, there is a subview which is a list of text. Once a data element is selected, a tree-structured list of text belonging to the path to the decision boundary is displayed. This list gives, for each text, information about the uncertainty of the prediction, the classification, and the ground truth class of the text. Data elements can be selected from this list too. On the right side of the locality view, we provide a list of the most relevant words of the locality. This list gives information about the possible importance of the words for the prediction. We also propose a subview where users can find the 2D projection from UMAP, TSNE, and PCA. In this projection, we include Voronoi cells to show the decision boundary. As you can see, the boundary with UMAP for this locality is not a straight line. Finally, we propose a confusion matrix, as well as an area where users can classify inputted text to view how changes in the text can influence the prediction. The position of the yellow line in the boundary subview shows the position from the decision boundary. For this text, for example, it means that the prediction has a very high uncertainty because the yellow line is right next to the gray line, the line of the decision boundary. There are many interactions in A/B text, allowing users to find a lot of information about the rule learned by the neural network in the selected locality. In this example, I will show in 2 seconds that you can see data elements which contain which rule just after the classification. So you can see up here. So you can see data elements which contain text and maybe the position of these data elements compared to the decision boundary. And here, for example, we modify slightly the selected text and we see that the uncertainty of prediction is a little bit higher. I will now present a case study for A/B text. In this case study, I will show how A/B text proves that a neural network was able to capture nuances in the review of products sold on Amazon. Green data elements are positive review and should be placed on the right of the decision boundary. Orange data elements are negative review and should be placed on the left of the decision boundary. In the bottom left of the screen, there is a UMAP projection of the locality. The grid rectangle contains all the text displayed on the right. We cannot see the uncertainty associated to the prediction in this view. In the top left of the screen, there is the right side of the decision boundary. You can see it on the left. All text belonging to pass from the selected data to the decision boundary are displayed on the right. As you can see, they are all classified correctly. I choose 3 texts from one path from the selected data to the decision boundary, the blue one, the pink one, and the green one, and I will read them to you. The first one, the blue, is the book came in a short amount of time and was in great condition. The pink one is the book came in just after a few days and it was in a great condition. Sorry. The last one, the green, is the book came in the condition that was listed and I received the book within a few days. As you might have noticed, I read the review from the most positive to the least positive. This is also the order from the far away from the decision boundary to the closest to the decision boundary. It proves this that the neural network was able to capture nuances and to classify text according to these nuances. A last example of that is the selected text in the top of the screen. The book came fast, right at the time I needed it, and it was in great condition. It is the text that is the most positive review, and it is the far away from the decision boundary. As contribution scores are widely used in literature to explain prediction for textual data, we include them in A/B text. Here, for example, we use attention score of an RNN. To conclude, I will say that A/B text helps increase interpretability of neural network by explaining predictions through many localities. It can be used to control the neural network quality. I will add that A/B text is not only useful for neural networks, but it can be used with many classifiers. And concerning our perspective, we want to extend the visualization of the decision boundary for neural networks to a multi-class classification. We also want to try different data types, add justified explanation and data generation to explain predictions. Thank you all for your attention, and I will be happy to answer your questions. Thank you.
Thank you very much, Alexis. There's one question, actually that's one I also noted down. You mentioned that you could probably extend that to a multi-classification problem. Now, if I look at all the things you described in your paper, they are very much focused on binary classification, I would say. So any ideas how this could be done?
Yes, thanks for the question. It's a really good question. And to do the multi-class classification problem, we will have to identify the place in the representation space where you data elements go from a class from another. So we'll have some hyperplanes which cut each other, and we will have to project data elements on the closest decision boundary between two classes. And then, for the visualization part, we'll have to use a referential, maybe a data, maybe a frontier, maybe a group of data to visualize multiple decision boundaries or one decision boundaries depending on the reference chosen.
Okay, thank you very much. Since there are no more questions and we are also running a bit out of time, please, let's start right away with the next thing and thank our speaker again. Thanks, yes. So the next topic will be legal viz, exploring and inferring precedent citations in legal documents. And the speaker will be Lukas Resk.
Hi everyone, I'm Lucas Hesk, and I'm going to present the paper Legal Viz, Exploring and Inferring Precedent Citations in Legal Documents. The key question I want to answer in my presentation is, how can judicial experts explore citations in a large number of Brazilian legal documents? The Brazilian Supreme Court, STF, is the highest court in Brazil, and it's primarily responsible for guarding the Brazilian Constitution. Historically, Brazil has always had an overloaded judiciary. For instance, in 2004, there were over 100 million pending cases. Furthermore, because decisions on similar cases can conflict, there has always been a climate of legal uncertainty. To approach these problems, the National Congress amended the Constitution in 2004, allowing STF to create binding precedents, also called BPs. These precedents consolidate understandings of judicial issues, and from 2004 to 2020, the court ruled 58 of those precedents. It is common for STF judges to cite binding precedents in their decisions. However, when analyzing these citations, lawyers and other judicial experts may face difficulties because of a number of reasons. A large number of documents with long texts, a difficult Portuguese legal language, and documents related to a BP but that don't cite it, what we call a potential citation. Consider the example of BP4, which deals with the issue of the minimum wage being used as an index. This decision explicitly cites the BP4 in the text. That is, this is an explicit citation. However, there are documents that do not cite the BP but have subject close enough. For instance, this document and the BP both cover the issue of the minimum wage being used as an index factor. The BP says, the minimum wage cannot be used as a basic index for calculating. And the document says, the prohibition of the binding of the minimum wage aims to prevent the user of that parameter as an index factor. They both cover the same subject, but in different contexts. This is what we call a potential citation. We notice that the explicit citation is easy to identify, but the potential citation is not trivial. Among the ways to explore legal data with visualization, two approaches stand out. The first one is visualize the similarity between parts of documents. Examples from literature include Pika and Text Reuse Browser, visual analytic tools that highlight similarities between texts in different domains. A more general approach is visual analytics applied to legal data. Examples from literature include NOLEX and EU CaseNet, which allow visual exploration of legal documents in the Italian and European contexts. However, the literature in these approaches has a few limitations regarding our research problem, and they do not present one or more of the following features. The incorporation of a machine learning pipeline for the inference of non-trivial citations, the visualization of explanations of machine learned model decisions, and the support for peculiarities of the Brazilian legal data as presented. In this work, our main contribution is LegalViz, a web-based visual analytics system designed to tackle the presented problems and ease the analysis of binding precedent citations in STF decisions by judicial experts. LegalViz's main features addresses the mentioned limitations in the literature because it incorporates a machine learning pipeline for the potential citation inference. It allows the visualization of machine learning model explanations, and it is designed to visualize Brazilian legal data. Now we cover the workflow of LegalViz. We first retrieve explicit citation information and filter representative decisions, MVPs, from our database. These data are used in an elaborated strategy to infer potential citations. Finally, the user can interactively explore documents that cite or could potentially cite binding precedents through the three visual components that compose our framework. The identification of potential citations is modeled as a classification task, where the classes are the precedents being cited. To achieve this, original documents suffer text preprocessing. The processed documents are converted into vectors in a high-dimensional space, and a classifier algorithm is fitted in these vectors, learning what makes a citation. Documents without split citation are fed into the fitted model and have the probabilities of citations inferred. An interpretability technique acts to explain the citation inference, presenting visually the most important sentences. Regarding the machine learned part, after several tests with vectorizations and classifiers, we end up with a TF-IDF vectorization with dimensionality reduction and a linear support vector machine with 96% test accuracy. Regarding the interpretability part, we decide to use the method local interpretable model agnostic explanation, usually called LIME. Basically, it identifies the most important sentences for the potential citation assignment, informing our system to highlight them with a background color scale. Let's now see a demonstration of the system. The interface of LegalViz is composed of 3 linked views that complement each other. The first one is the global view, which presents citations to binding precedents in decisions from the Supreme Court. The 10 most cited BPs represent the y-axis, while the x-axis represents the publication date of BPs and decisions. The red markers indicate the publication date of the BP, and the bar height indicates the number of citations. The type of citation is represented by colors. Blue means a split citation, orange means potential, and both colors mean both types. Users can apply several types of filtering, including type of citation, process type, and just reporter. Let's first explore a split citation, and after, a potential citation. Clicking on any bar, we are presented with the paragraph similarity view, in which the documents with the citations to that BP in that date are displayed in the y-axis. Each document is divided into bars in the x-axis, corresponding to the paragraphs, with the color intensity corresponding to the similarity between the paragraphs and the binding precedent text. See that the first document has a very dark blue paragraph, which means a high similarity with the BP text. Clicking on this paragraph opens the document reader view, in which the user can explore the raw text of the document. If we hover the paragraph we clicked before, we are presented with a tooltip comparing the common text between the BP and the paragraph in yellow background. We note that both texts are the same, that is, the paragraph contains the BP text. This is a common pattern for binding precedent explicit citations, and the system is able to help explore the citation pattern. Let's now explore a potential citation case. In November 2004, there was a potential citation to BP4 because of the orange bar. However, this BP was only created in 2008. Clicking on any paragraph of this document brings the decision text to the document reader view. Because this is a potential citation, the document reader will also present the model explanation for the potential citation assignment through a background color scale, indicate the most important sentences for this assignment in green. Hovering over a paragraph with one of the most important sentences in green, we note that this paragraph says, "The prohibition of the binding of the minimum wage aims to prevent the user of that parameter as an index factor." This is also the subject of binding precedent 4, which says, "The minimum wage cannot be used as a basic index for calculating." Because both the document and the BP cover the same subject, although in different contexts, one can point out that this is a valid potential citation. Okay. To assess the usefulness of LegalViz, we recruited 6 domain experts not involved in the tool's development to perform a user study. They work as attorneys, researchers, legal assistants, and trainees, and have from 1.5 to 22 years of experience in analyzing legal documents and binding precedents. After methodological interacting with the system, users were asked to answer a list of quantitative and qualitative questions. The quantitative questions evaluated several aspects of LegalViz methodology. Examples of quantitative questions include: it is easy to filter interesting decisions for analysis. It is easy to identify parts of decisions related to the BP of interest, and LegalViz is useful. The table presents for each question the percentage of users who agreed to them or not. The major agreement in all questions indicates positive feedback. The general feedback in the qualitative questions was also positive. In our work, there are some limitations planned to be tackled in future work. For instance, we only approached the 10 most cited binding precedents from the set of 58 ruled by STF. This is because the majority of BPs have a small number of citations in the dataset, so we can train models. To tackle this problem, we intend to apply data augmentation methods. Currently, we do not collect user relevance feedback about potential citation inference, and we do not visualize the uncertainty of the model assignments. We plan this for future work. Finally, there are other limitations in our work regarding the improvement of the machine learning pipeline that are intended to be approached in future work. For example, the training of language models in Brazilian and Portuguese legal data. Thank you very much for your attention. You can find our paper and more information in this QR code or link.
Thank you, Lucas. And we have one question on Slido. You mentioned that you use TF-IDF with SVM after tests. Which other models did you test?
Okay, thank you for the question. I couldn't present, because of time constraints, the models part, but I have a backup slide here with the model results. So this is a table presenting a list of the models we tried and also the performance on the validation set. So as you can see, we tested linear models, language models, and other embedding models. And in our data set, the TF-IDF with Sport Factor Machine had the best performance. In our paper, we discussed these results and the reasons why we think this occurred. Refer to the paper for more information, and thank you for the question.
And maybe one final question. How difficult would it be to update your system with new BPs? Let's say ones that are well-formed in terms of not being skewed or...
Interesting question. If this BP has enough data to train the models, we only would have to train these new models for considering this BP also, and we could update the system. The problem is that if a new BP is created today, for instance, we won't have data to train the models. So this is a problem we plan to tackle in other ways.
Okay, let's thank Lucas again. And with this, we hand over to Xingbo Wang, who will be presenting dHumor, visual analytics for decomposing humor. This, of course, is especially important for German session share. As everyone knows, we don't have humor, so maybe...
It contains a German joke, hope it does
Okay,
not offend.
even better. Stage is yours.
So hello everyone, I'm Xingbo Wang from Hong Kong University of Science and Technology. Today I will present our word dHumor, visual analytics for decomposing humor. Humor is a powerful communication skill for public speakers to connect, engage, and entertain their audiences. Successful use of humor requires a mixture of both engaging content buildup and appropriate vocal delivery. Thorough understanding and the learning of humor can only be achieved if we can decompose this kind of building blocks and interactions between them. Prior works such as Schopenhauer's incongruity theory has qualitatively characterized humor. However, they are too abstract to study concrete humor examples. Based on this abstract series, researchers adopt computational approaches to quantify humor. For example, in the sentence, a clean desk is a sign of cluttered desk drawer, the word pair clean and cluttered expresses incongruity. However, these features are not comprehensive. They focus on either verbal or vocal aspect, while both ends are needed simultaneously. Moreover, the humor features usually target short jokes such as one-liners, overlooking longer-term build-ups. Furthermore, multi-level features and their sophisticated interactions hinder humor understanding. To address the challenges, we built a visual analytics system to help domain experts conduct a systematic multi-level exploration of multimodal humor features. Our goal is to support an in-depth and systematic investigation in the humor composition and its vocal delivery in public speaking. We expect our system to alleviate mental burden when analyzing unstructured humorous speech. After literature review, we interviewed 7 users to validate a set of humor features and collect their analytical needs. Finally, the important textual and audio features and system design requirements are summarized. First, the humor-related features are presented in the table below. I will introduce the computation and visualization later. According to the user interviews, we identified that users generally analyze the speech for the whole to the parts, and the analysis follows the language strata from context to forms. The word usage and vocal delivery with the highest importance rankings were considered essential for humor analysis, while the humor build-ups were considered most difficult part. Besides, we distill a set of design requirements to support this multi-level exploration of humor features from speech, context, and sentence levels. Our system pipeline is shown as follows. We first collect humor speeches such as TED Talks, stand-up comedies. Then, given the humor speech, we segment it into different humor snippets based on the occurrences of humor laughter markers in the speech. For each snippet, we compute textual and audio features. Finally, these features are visualized in an interactive analytics system. Next, I will introduce the humor feature analysis and visual encoding. At the sentence level, we compute textual features including incongruity, sentiment, and phonic styles. The semantic incongruity can be modeled by repetition and disconnection based on the semantic similarity between word pairs. The words express strong polarity and subjectivity will be highlighted to indicate sentiment, and we extract alliteration and rhyme chains to represent phonic styles. Besides, we extract and encode the following 4 representative audio features that reveal the speaker's vocal delivery style, including speed variation, pause, volume variation, and pitch stress, and we highlight the corresponding words with the inline annotations. To reveal the relationship among build-ups of a punchline, we target one essential comedy device, that is repetition. For example, the punchline sentence number 6 tells that Germany does not have fantastic food. The repetition of Italy and Germany in the context emphasizes the speaker's main focus of comparison. Different modifiers and no before the repeated stigma for being evil highlights the opposite repetition of Italy and Germany after World War II. The comparison is carried on and reviewing the punchline, implying that German food is worse than Italian food. To capture inter-sentence repetition, we first extract sub-phrases, for example, verb phrase go after and noun phrase the Italian community by traversing the dependency trees. Then we merge these phrases based on their semantic meaning and co-reference relationships. Then we design a context linking graph to visualize inter-sentence repetition within the humor snippet. Specifically, the context summary is placed at the top, where each sentence is encoded as a rectangle. Under each sentence, the number of stacked bars represents occurrences of repetition in this sentence. 2 sentences that share similar concepts will be linked together. Then, the repetitive concept overflow among multiple lines in the middle, and the sentence details are placed at the bottom. At speech level, we design an augmented time matrix that provides an overview of the distribution of humor occurrences and the humor features. Specifically, we combine the feature summary in A with the content summary in B. In A, each row represents a punchline. The color at the cell indicates a feature frequency. Darker color indicates higher frequency. In B, the content keywords are extracted and placed from top to bottom according to their occurrences orders. In the augmented time matrix, we have an additional summary of the total occurrences of humor features at the top. For each punchline, the summary of textual features, dark green bars, and the audio features, light green bars, are placed to the left. And the speech content word as well as the frequency are placed at the right. Next, I will walk through our system using a video demo.
In the beginning, a user named John feels interested in humorous speeches about personal experience. He refers to the control panel and finds speeches that are related to this topic. He further sorts them according to the total occurrences of laughter in the speech. Then, he clicks the first speech named, "Apparently You Can't Pretend You're a Cop." He observes clusters of punchlines in the augmented time matrix that are close to each other across the whole speech. And he wonders what words the speaker used and how the speaker delivered these short jokes. Then, he adjusts the filters in the humor focus view. He discovers that one punchline at the beginning has rich humor features. He feels interested and clicks on the time matrix to locate the corresponding humor snippet. Within the snippet, he notices that "cop" repeats 3 times in a question-answer conversation before the punchline. By examining the corresponding sentences, he realizes that the speaker showed up to a crime scene. He was asked by the people there about whether he is a cop. To avoid explicitly making an illegal claim that he is a cop, he quoted a common trope for police in movies and TV to mislead the people to believe that he is a cop. Specifically, John refers to the feature annotations and finds that the speaker raised his voice on the first few words of the punchline. Then the speaker paused a little bit before revealing the essence of the content: "I will ask the f***ing questions." In the end, he strengthened his anger through a tone particle, "okay." He clicked the sentence to refer back to the original video clip in the humor focus view.
And I go, "I'll ask the questions, okay?"
After checking the original video, he confirms that these annotations help reveal the verbal and vocal patterns of humor.
We conducted case studies and expert interview for system evaluation using a TED Talk and stand-up comedy. For each speech, they need to find words of interest at speech opening, humor features of interest at speech closing. When analyzing each snippet, they need to reason about what contributes to humor. According to their feedback, they appreciate context linking graph for traversing and summarizing humor buildups. They especially like the straightforward inline annotations. Moreover, the multi-level exploration aligns well with their analysis flow. They usually examine incongruity features to identify the humor essence, rely on pitch and pause to see key delivery patterns, and use verb and noun phrases to gain an overview of the story development. The negatives mainly involve inaccuracy of feature extractions, especially incongruity. Also, participants say that they might not remember all the visual encodings, and the augmented time matrix was the most complex view. Through the design process and evaluation, we know that social contexts are important for humor understanding. A complex summary of humor multimodal features is helpful for multimodal analysis. Our system can be extended to investigate other audience responses, and also the context linking graph is useful for text analysis. In the future, we would like to add visual features and other contextual features to enrich the humor analysis. In addition, we can consider alleviating the inaccuracy of feature computation by using advanced models and visually encoding model uncertainty. So that is all. Thank you. I'm currently on the job market. And this week, we have 2 papers about multimodality of natural language. Currently, my mainly focus on the interpretability and analysis of natural language models, and also natural language as user interactions and feedback for applications. So if you're interested in my work, please visit my project page and homepage for more details. That is all. Thank you.
Thank you very much, Xingbo. And we got a number of questions on Slido. Maybe let's start with one. I think it was not so clear how the multimodality works. So there is one question where the laughter markers come from.
So this laughter markers is because these videos we crawl from the YouTube. And YouTube have lots of these kind of called audience reaction markers. And this kind of markers also have because they are time stamped. So we can get the time of the occurrences of this kind of laughter. And also, in the future, if we want to fully automate this kind of process, we can use laughter detection models to help us to find those moments of laughter. Yeah.
Okay, thank you very much. And maybe another question that's related to this, could you also use an additional modality, like for example, the gesture that could be extracted from a video? Would that be something to improve the system?
Yes, we have a paper about gesture usage and how it it cooperates with the data content at another session which called, I think it's decision making and reasoning session. Yeah, you can also check out the papers for more details.
Okay, thank you very much again, Xingbo.
Thank you very much.
And there are also more questions in Slido, so please feel free to come after the session and ask Xingbo directly. Okay, with this, we go to our next talk, which will be interactive and visual prompt engineering for ad hoc task adaptation with large language models. And speaker will be Hendrik Strobelt.
It seemed to work. Okay, thank you, Stefan, for the introduction. So I'm going to talk about interactive and visual prompt engineering for ad hoc task adaptation with large language models. And you might rightfully ask, wait, what? Let's start from the beginning. So imagine you come up with a very ad hoc language classification task. Yeah, so you didn't have this before, and all of a sudden, I don't know, a client comes to you and they're like, okay, I have a bunch of documents and I want you to classify them between, here in this case, news. I want to classify if it's sports news, world news, business news, and technology news. So how you would go about this is actually determined by which kind of NLP pipeline you want to use. Yeah, so here's a little bit of an overview of kind of classic and historic pipeline, including what is now actually state of the art. It's from a report that's not yet released, but will come out soon. So on the left side, you see, as said before, the classical pipeline. You do one step after the other. Yeah, you do sentence splitting, word splitting, post tagging, blah, 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 the stuff that you know from ages ago. Or you can train an end-to-end model, a small language model, so to say, or mid-sized language model. But this requires already a lot of data. Yeah, especially a lot of labeled data to actually train this model. And if it's just about, I don't know, 100 documents that you can get labeled, this is not really a feasible option. Or you can resort to large language models. If you want to fine-tune them, you even need more and more data to actually fine-tune the model. But you also need a lot of compute. Yeah, so you burn a lot of money. So what the NLP community actually found out is that there's a third way. So you can use a large language model and use what is called prompting or zero-shot learning, or however you want to name that. And I will show you how this works. And it's actually much simpler than you can imagine. Oh, this is the slide that you never can miss in a talk like this. So what does large actually mean? So you see essentially kind of the Moore's law of NLP models here. So every year you have a 5 to 10-fold increase in numbers of parameters these models are trained on, which also leads to the effect that they do not only learn about like general rules about NLP or linguistics, they actually also start to memorize more and more like world knowledge, etc., depending on what they were trained on. So now imagine you have a large language model and you start training it on a natural language standard task like summarization or paraphrase identification, question answering, etc. And you do it in a way that you encode in the training data the formulation of the task itself. So you essentially, you fine-tune a large language model in a way of that you say, for summarization, you give it the sentence, the picture appeared on the wall of a blah, 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 blah. And then you say, how would you rephrase that in a few words? And the ground truth label to this is actually the summarization of the aforementioned text. Yeah, so this is following the blue path here. Another example for the question answering, the yellow path. I know that the answer to what team did the Panthers defeat is in the Panthers finished blah, 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 blah. Can you tell me what it is? And you provide the label Arizona Cardinals. So you can train a large language model that is trained on these standard language tasks. In this case, it was a modified T5 model from Google, refined to a T0 model, part of the big science project. The interesting observation is that now you can even task the same model with new tasks that it hasn't seen before. And again, this is not just a new data item. This is a complete new task. Yeah? You ask the model to do something completely different, and yet it still might be able to solve this task. Yeah, and this is actually the magic or the voodoo of prompting. And how you do this is even simpler. You just formulate the task. Yeah, you say, suppose the banker contacted the professors and the athlete. Can we infer that the bankers contacted the professors? And you might get actually the model to produce as a text that says yes. Yeah, crazy. Coming back to our problem. So we could do now the following and say, face the same model that I just showed you, T0, say like, in which section of a newspaper would the text appear? News article, colon, and then you provide the text you actually want to classify. Yeah. And then you observe the productions of this model, and you just figure out which of the 4 possible options is actually highest ranked. Yeah. So you do not only observe what the model actually produces as a text, you already know which 4 options are interesting to you. You just choose the one that is highest or has the highest rank. And in this case, sports news has a higher rank than worldwide news. And then you say, okay, maybe this is about sports news. Okay, easy idea. Well, we could be done here. Unfortunately, there's an infinite variation of how you can formulate the questions and how you encode your task by using natural language prompts. Yeah, just examples here. So you want to figure out, like from a small subset or from a subset that comes to your mind, which one is actually the best prompt? Which prompt variation performs best, only given a small set of data that you can label. Yeah, so you want to attach some kind of attribute to it that determines good, bad. And this is exactly what prompt IDE is for. Yeah. So this tool helps you to explore prompt variations, figure out which variation of the task formulation performs best on the given task. And in this case, the task is classification. And I think time allows. I'm going to give you a quick demo. So here we have specifically the task of finding out if a text is world news, sports news, business news, or technology. Here's an example text. Yeah, Wall Street, bears claw back into the black, Reuters. So this is typical news text. It is also labeled with a number 2, and the number 2 refers to an index of 4 possible answers, world, sports, business, or sci-tech. And this is data that you ask people to label for you. Again, small world regime, yeah? 100 texts or something like that. And then you have a prompt template where you say, first I want to include the text, but I also want to include 2 variables that allow variations of formulating the task. A variable Q2 and a variable Q1. Q1, underlined red, is the formulation of a question. Q2, underlined with blue, is just indicating model, here's a news article, or model, now here's raw text. This is just a little prefix, yeah, nothing important. And what we can do now, I don't explain the other fields, it's just too complex. What we do now is we run these 10 variants of prompts against a couple of samples. And you see this is kind of progressively updating and always giving you the variation or the formulation of the prompt as first item that performs best, yeah, on the observed samples. And while this is doing, you can already look into it and you figure out, okay, I've done enough, I've burned enough GPU hours. You can look into detail for this specific prompt variation, and you figure, yeah, it's doing well. Whenever you see green, right classification, but you also see that here's an example where the label would have been business news, highlighted in, with green borders, but what the model actually thinks it should predict is technology. So it's a misclassification, while the model itself produced business as text. And with a little bit of statistical knowledge, you know that the longer the texts are, the less likely it is that they are on top position. So what we can do is We can even go down here and say, okay, instead of adding news to all of these thingies, let's just use the regular words as classification labels. At the end, it doesn't matter, what kind of words you use here, because you can always make them look better afterwards. You just want to have the highest possible performance. Okay, and then you can observe again, like samples coming in here, and it does actually a pretty good job. Okay, let's say this is a good prompt that worked on very small set of samples pretty good. You can go to refinement and run the same thing against a larger set of samples. So you go from very small regime to mid-size regime. When we do this here, so it takes a while. And then you see actually what you would expect. You first get a little bit of performance, 60 right, 40 wrong. You get a confusion matrix, and you see that actually here on the diagonal of the label technology, there's something wrong. So it didn't get any technology news right. And we observe now that for the label technology, or the label that we choose named technology, actually the word science was very, very often produced. And again, we can go back and call this whole thing science instead of technology. Again, doesn't matter how we call it later. And test this whole thing again. And to take the suspense out, it should perform better. Here we go. See, we have a pretty good diagonal. So maybe it's a pretty good classifier, and then you can also, it's automatically saved in a card. You can export it, and you can immediately apply the classifier to a problem, to the problem you just stated. So this is what kind of the ad hoc task means. Just let me finish with two or three final remarks. And in terms of design decisions, you saw there's a lot of text. So the question is it visualization? I leave it to you to answer that. We spent a lot of time thinking of which kind of templating language we use. So we looked around what others used and just copied what their approach is. We also had first a coloring of all answer options, but figured when talking to the domain experts, they wanted to know if it's right, aka lit it up in green, or if it's wrong, leave it gray. So the other colors didn't matter to them. Another question, I'm already going into the question section probably. Why would you use a manual search for a prompt if there are automatic methods out there? And this is just a tweet from yesterday. I love it because it's from an NLP person, and they said like, well, these things allow you to create human-readable prompts, and human-interpretable prompts. So there's a specific need for these. And if you look today at Twitter, there's my collaborator, actually, Sasha. They just brought out a paper that says, explaining patterns in data with interpretable auto-prompting. So they search for these explainable prompts automatically. Maybe my system is obsolete. Who knows? With that, thank you very much, and feel free to look at Prompted with Up AI.
Thank you very much, Hendrik. So there are quite a number of questions popping up.
Sorry.
Yeah, don't worry. I mean, that's good. So maybe one of them, would a user of this tool be someone training a language model, an expert in the text and in the text task domain, or both?
So typical user that comes to mind is data scientist. So someone who's like having client contact, and they say like, can you hack something quickly to do this classification? And I mean, this is an 80-20 solution. So 80% accuracy, I think, is achievable. If you need better performance, then of course you have to probably go down to route of training your own model and acquire more labeled data, etc. But this is for the quick round. Data scientists, I think, is the best.
And maybe very briefly, also another important one, I think, because this seems not to have come through. Could you imagine a way in which the user could get insight into how to change the prompt? Maybe one could show what part of the input model output can be attributed to.
So far, the system doesn't give you too much insights besides the thing I showed you that the label name might be wrong, which I think is already very helpful. And this was actually the one that NLP experts also liked the most. They haven't seen something like this before, but of course, there's room for improvement. I put it on the future work list.
Very good. Let's thank Hendrik again.
Thank you.
And I'm sure there will be more questions after the session. So then let's go to our final talk. This is something completely different, actually. The title is A Hybrid In Situ Approach for Cost-Efficient Image Database Generation, and the talk will be given by Steffen Frey.
And welcome everyone. So my name is Steffen. It's my pleasure to present joint work done together with Valentin Bude, Matt Larson, Tom Ertl, and Hank Childs. And traditionally, visualization follows a post-hoc paradigm, which means that generated data is saved to disk, which is then accessed at a later point in time for visualization. However, as you know, this doesn't really scale to large simulation runs, as data can be generated at a much higher rate than it can be transferred or stored. Therefore, it is increasingly important to visualize results from supercomputers in situ, which means that visualizations are generated while the simulation is running. This work specifically considers a popular instance of in situ visualization, namely the generation of image databases in the style of the Cinema project. An image database consists of a collection of renderings, and in our case, each corresponds to a different camera position. Creating an image involves two types of operations: the rendering of sub-images from data partitions corresponding to different nodes, and the compositing of those sub-images to yield the final result. There are many possible instances of in-situ processing, varying over division of resources, access to data, as well as other factors. Two instances in particular are widely considered in practice. In inline in-situ, the simulation code and visualization routines run on the same compute nodes, which means that they access the same memory and alternate in their usage of a node's cores. The other one's in transit in situ. Here the simulation code and visualization routines use distinct resources, which we refer to as simulation nodes and visualization nodes. Simulation nodes generate the data and send it to the visualization nodes via network communication for them to do the visualization work. Unfortunately, both approaches exhibit various types of inefficiencies. For example, inline is susceptible to issues when costs of visualization are heterogeneous. This means that it takes various amounts of time to render images from different data partitions. Right-sizing the number of visualization nodes is an issue for in transit. If there are too many visualization nodes for the desired task, they sit idle. If there are too few, then either tasks need to be dropped or the simulation nodes need to wait, as in the shown example. These issues are made worse by the fact that typically the data across nodes changes significantly as the simulation progresses, so this is very dynamic. Of course, with this, the cost of visualization tasks also shifts during the course of the simulation. This results in inefficiencies, and to address them, we propose a hybrid between traditional inline and in-transit techniques. Conceptually speaking, this means that we have dedicated visualization nodes, such as in-transit approaches, and simulation nodes can also take over rendering tasks, such as in inline approaches. The main challenge for hybrid in situ is the optimal distribution of tasks. In our work, we take the following basic approach. The rendering of images is flexibly assigned to either the simulation node or dedicated visualization resources, whereas compositing that collectively considers all partial images from a camera configuration is only carried out on the visualization nodes. The basis for the distribution of rendering tasks are timing predictions concerning all relevant parts of the system. Particularly challenging, though, are estimates for render timings, as they vary significantly depending on the data that is generated on the corresponding node. We use probing to achieve sufficiently accurate prediction, which means that we complete a certain number of randomly selected rendering tasks to estimate the overall cost. For work distribution, our load balancing scheme initially assigns all rendering tasks that remain after probing to the visualization resource, and then the balancing scheme iteratively shifts render load to the simulation node with the currently lowest total anticipated runtime. And we do this until runtimes are evenly balanced across all simulation and visualization nodes. To evaluate our hybrid in situ approach, we use TextMP2 supercomputer and consider two simulation codes, Cloverleaf and Nix. We quantify efficiency by the number of node seconds spent for each so-called megacycle that includes both simulation and visualization work. I'd now like to start with cloverleaf results and a standard configuration with a visualization to simulation node resource ratio of 1:8 and a generation of 144 images for the database. You can see that hybrid in situ reduces idle times and with this significantly increases the efficiency of the whole process. When looking at the impact of increasing image counts generated at each megacycle, we can see that the gains with respect to inline and in transit increase accordingly. The reason for that is simply that our hybrid technique has more opportunity for cost savings when there's more work, and there's more variability that we can reduce and more flexibility for dynamic distribution. We now extend the study with different ratios of visualization resources. Of course, this only impacts our hybrid and the in-transit technique that makes use of such dedicated resources. We observe that our hybrid in situ approach can also flexibly adapt to different numbers of dedicated visualization resources, at least as long as there is enough visualization work to occupy these additional resources. When the amount of work per visualization node becomes too low, then these nodes will still have to sit idle while the simulation advances. Next, I'd like to present a weak scaling study using up to 19,200 logical cores with the NIC simulation code. It compares our hybrid approach against pure inline. Most prominently in this study, the inline approach devotes more and more time to compositing due to pure scalability, which you can see in yellow here. But our approach suffers from this as well, but to a much lesser extent, as only visualization nodes are involved in the compositing. While there are increasing transfer and copy times with hybrid, we can see that significant savings can be achieved across small to high core counts. In conclusion, we propose a hybrid between inline and transit techniques, and it reduces 4 general classes of inefficiencies that we identified with inline and in situ visualization methods. Variability is an issue caused by heterogeneous visualization workloads. In our case, this concerns varying render times that you have from data that stem from different simulation nodes. Hybrid in situ addresses this inefficiency by dynamically distributing work to other resources. Limited scalability can be an issue for some operations like compositing with large node counts. And hybrid in situ tackles this by limiting this operation to the smaller set of visualization nodes. It is challenging to pick the correct ratio of visualization to simulation resources for in-transit techniques. And hybrid mitigates this issue as it allows work to be shared across both simulation and visualization nodes. Finally, the overhead of transferring data from simulation to visualization nodes can be hidden by overlapping it with visualization work on the simulation nodes. In sum, addressing all those 4 inefficiencies allows us to save precious supercomputing resources. There are various directions for future work. First of all, we could potentially improve our current approach for generating image databases in different ways. For instance, our approach exhibits 2 main parameters. On the one hand, the ratio of visualization nodes, and second, the ratio of work items that we use for probing. They are currently set manually, but could also be determined automatically with a small prior test run. Cost prediction in particular is a very important basis for dynamic work distribution, and more advanced approaches in this direction could help us to yield even higher efficiency. Crucially, note that while in this work we tackle the generation of cinema image databases, our technique is generally applicable to in situ visualization settings that can be split into many small tasks for dynamic distribution, potentially also requiring additional communication. The image database generation considered in this work demonstrates benefits for a combination of a large number of independent tasks, so this is image rendering tasks, as well as reduction tasks, so the compositing of partial results. I want to end with a sequence diagram of our hybrid in situ system. Thanks to various parties for their support. Thank you very much for your attention, and I'll be happy to take your questions.
Thank you very much, Steffen. So there seem to be no questions. maybe this was a big step from the language models to in situ.
Yeah, sorry about that.
It's not your fault. So then maybe I have one. As you know, I'm an expert in situ. Not. So, but what I would be interested in is whether you could not just record images from the simulation, but if you had like more hints or features pointing to parts where the simulation shows really interesting things, could this somehow be integrated into such a recording strategy, and would that also work for hybrid approaches?
Yeah, that would, I think that would be a quite interesting approach, to have like a more targeted visualization of the parts of the data that matter. So this would of course make our approach a little bit more complicated. And on the one hand, in particular, with regard to our prediction approach, because what we currently do is we just like sample view directions from a sphere, and so we can get away with a relatively simple probing approach. If we have more targeted approaches, we also increase the heterogeneity that we have when we generate each image. So this means that we would have to like come up with a more clever, maybe some importance-based sampling approach in order to get our prediction results with few images, because that's a quite important part actually for us, because of course the probing step, the images that are generated during that, they are useful. We use them later on, so nothing is thrown away. So that is nice, but the more images that we need to sample for probing, the less flexibility do we have for dynamic distribution later on. So that's kind of an important part, also something that we focus on in future work, trying to get this number of images that we require for probing down.
Let's thank Steffen again. And also let's thank all of the speakers of this session and all the authors. Again, please. And I would like to thank the AV operator and the student volunteer. Thank you very much for helping with this session.